Hello everyone. Fortunately, I was able to find the USB-C adapter, so my microphone is working well. This video is going to be on the Sequential Bootstrap from Marcus Lopez de Prado's Advances in Financial Machine Learning book. I kind of regret suggesting I'll make this video because it is a lot of work, but I just want to basically illustrate the big picture concept, and hopefully in then another video we can basically implement this. Because as is, the code I kind of mostly took from Lopez de Prado's book will not work for a big enough data set. So I'll show you how to update sklearn to make it work. But for now, we're just going to talk about the big picture concept. So let's see if we understand this. So just to remind you guys, remember we talked about the whole idea of concurrent labels. Basically, two labels are concurrent if they have some overlap. So mathematically speaking, let's say label y and yj are concurrent at time t when both are a function of the common return at time t, rt minus 1 to rt. So basically, both of them have that in their label, right? They have that the time from t minus 1 to time t in their label, right? So then Lopez de Prado's book talks about a few concepts like total number of concurrent labels at time t, basically is the sum of all labels that overlap between, have a return between t minus 1 and time t. So basically, whenever there's a return from time t minus 1 to time t, you add all those labels up, the number of such labels, and that would be the number of concurrent labels at time t. To get the uniqueness of label I at time t, you basically divide by the number of concurrent labels at time t. So it would be an indicator function if that label depends on the return from t minus 1 to time t, divided by the number of labels with returns from time t minus 1 to time t. So then he defines the average uniqueness of label I to basically be the average of these uniqueness scores over the label's lifespan. So whenever this indicator is 1, meaning the label is a function of the return from that t minus 1 to time t, you average out these uniqueness scores. And then the total uniqueness overall for the data set is these average uniqueness for each label divided by the number of labels, basically. So the average over the number of labels. So set it shown visually, which makes a lot more sense. Something that looks like this, basically labels, you have a label here, the triple barrier. Remember, if you see here, the label 1 and label 2 are concurrent at all these return points because they have all these in common. And label 3 has a lot in common here. And then label 4, for example, is completely unique. There's no overlap. And if you zoom in a bit, maybe my zoom tool doesn't work, you'll see that label 3 here has things in common with label 1 and 2 in this section, sorry. So this has 3 in common. So anyways, just to remind you guys some of the key concepts. Okay, so why do we need the sequential bootstrap, what it is? Let's just remind you guys why the bootstrap and why, let's say, random forests, which are based on the bootstrap's method, work in the first place, is because there's this idea of the bias variance decomposition. So I don't know if you guys remember in an early statistics class, you can basically have the expected prediction error as a function of the bias squared plus the variance plus the irreducible error. So basically, and I skipped the algebra here, but I can do it in another video because I do like showing all the steps. But basically, the prediction error is basically so your function is basically f whatever this thing is called of x, and y is the label. So basically, the expectation of the error, basically that's the prediction error. The y is the actual, f of x is the estimation, is the bias squared, which is the expected value of this f hat of x minus f of x, that thing squared, plus the variance, which is expected value of that f hat minus e of f hat of x squared, plus some error you cannot do anything about. It's the irreducible part. So anyways, how does the bootstrap work? And we'll talk about it in the idea of decision trees. So for decision trees, let's say you have R, which I called it a random forest. Sorry, I meant in the context of random forest, or a bagging classifier, which the only difference is random forest. Well, bagging can work for any estimator, but like random forest uses bagging with decision trees, which is the most common. But it also selects a random number of features for each tree as opposed to all the features. So like if R is your random forest and random forest is like a sum of these TI, which are the individual decision trees, which do the bootstrap with sample. So 1 over n of that's your random forest. So basically what happens is like you have a bootstrap sample. So each tree is built like you have n points and you randomly select with replacement from that n. You have n trees, but like you have, let's say, m data points, m, not n. So you randomly select from replacement from that set of m, as I spoke about in the random forest video. And basically, you train a tree on that bootstrap sample, and you train n such trees. You take the average, and that's your classifier. So if you look at the variance of that classifier, if we look at some like old algebra stuff, you can say like, okay, you can there's a property you can do like 1 over n squared. You take the constant and square it, and then the variance of the sum is actually basically the variance of the sum is basically the sum of the variance plus the covariance terms. So it's 2 times whenever the TI doesn't equal TJ, meaning just the covariance terms, excluding, of course, when the tree when I equals itself, which is part of the variance thing. So if you assume like your trees have a covariance of let's say the trees are IID, they have a covariance they have a correlation coefficient of rho, so they have a covariance of rho sigma squared. You can kind of simplify this thing out. And sorry, I got a little bit mathy, but like you keep simplifying these things out, and eventually you get to this term here, which is this sigma squared, which is the variance of an individual tree, times 1 plus rho, which is the correlation between the trees, times n minus 1 over n. So what you're going to see here is basically this term is 1 over n. So this term will go to 0. So that will lower the variance completely. But this term will only go as n goes large to rho over n. So, to rho. So basically, we really want rho to be small for the variance to go down. If rho is large, meaning the trees are highly correlated, that means the algorithm is not going to work so well. So, so basically, like we need a small correlation. So by the way, that's why random forest, like the bootstrap sample adds 1 level of like making it less correlated, and then randomly selecting a certain amount of features make that even less correlated. Okay, and sorry if I'm speaking too fast. I'm sorry about that. So, but what's our problem? With the overlapping outcomes, as we've shown here, these bootstrap samples will be highly correlated, and that is not good for this formula. The variance reduction will work a lot less well. So remember in the previous random forest video, I showed you guys that like on average, if all the examples are independent, no overlap, roughly speaking, if n is large, the number of bootstrap samples, you basically on average, you will select a certain label with probability 1 minus 1 over e. But if there's a lot of overlap, the chances that you include like a certain part of a certain label becomes closer to 1. So these become basically highly correlated. I'm mumbling on and on. Bottom line is like when you have overlap, it's highly correlated, and it's not gonna basically the random forest is not gonna be as good, right? Because the correlation will not allow you to get rid of the variance. Okay, so so basically, like, what can we do about this to improve it for our sake? Okay, so Lopez de Prado talks about a few things. One, he talks about restricting the horizon. So if the horizon isn't like the triple barrier with like overlaps, the horizon is just like maybe one return at a time, or maybe like a certain fixed size and there's no overlap, we don't have this problem. And to be honest, he says it's a bad idea, but like in my experience, like sometimes this is honestly like one of the better approaches, to be honest with you guys, for me at least, for my modeling. Another thing is to drop overlapping outcomes. So let's say this is a stupid method, and that's what he says in his book. If you have these overlapping outcomes, maybe you can drops label 2 and 3, just keep label 1 and keep label 4. Drop 1 and 3, keep label 2 and label 4. But he says in his book that causes like a huge, basically loss of information, right? So that's a bad idea too. The other approach, he says, is basically sample according to average uniqueness. So this actually is actually a pretty good approach, and I actually always use this. So basically what he means here is basically, so like each of these trees, basically the data set is size like 1,000, right? So we sample with replacement of size 1,000. But here is saying is, okay, instead of sampling with a replacement of size 1,000 for this tree, we'll take it like max samples. We'll do like sample 100 instead, for example, right? So if we sample only 100, there's a lot less overlap. And that actually works very, very well. He suggests doing it as a function of like the uniqueness. But that actually works well, and I always use that, the max samples thing. In my personal things, I tend to always use that. So I actually do recommend that one. Okay, so that is definitely an idea that works pretty well. But he says what's better than all these things is basically a sequential bootstrap. And he talks about like there's like this old thing from Rao, which is one of the most famous statisticians ever. He basically had this sequential bootstrap idea. But let's talk about the one Lopez de Prado speaks about in his book. So the idea is, and I'm going to give you 2 ways to think about the sequential bootstrap. One of them is basically like first intuition, and second one is the second intuition. It'll make the code he's doing maybe a bit more understandable, because when you read it, you have to probably read it like 100 times to try to understand it. So let's try to see if this makes things a little bit more sense. Okay, so basically the idea is we want to lower the number of overlaps, but we still want them to be possible, because of course if we have so much overlap, then the bootstrap is not going to work as well. So we want overlaps to be less likely, to enhance like the average uniqueness of a sample, meaning the samples to be different. So the idea with the sequential bootstrap is basically like what you're going to do is you still want to get like your data set is a size like 1,000. You still want to get like a bootstrap sample of size of 1,000, but you're going to sample it a different way. You're going to give less weight to labels you already selected and to other labels that have overlaps with them. So let me illustrate this with an example. So let's say our data set is only of size 4, right? So in the first iteration, we're going to randomly select with probability 1/4 L0 through L3, right? And let's say we randomly selected L1. So what we're going to do now is we are going to basically, since L1 has overlap with L2, we are going to reduce the probability of L1 in the next sample, but we're going to also slightly reduce the probability of L2, the label 2, because there is some overlap with L1. So we're basically going to always reduce the probability of any labels we selected that have any labels that overlap with the label we selected. So how are we going to reduce the weight? So L0 has no overlap with L1 and L2, so the weight is still, relative weight is still 1. But L1 now is the one we selected, right? So we're basically going to, instead of having this be like 1, 1, and 1, it's going to be 1/2 plus 1/2 plus 1/2. You're going to basically do 1 divided by 2 Previously, it was 1 divided by 1. I know this is a little confusing, but the idea is now you'll take the average of that, and you'll get a half. So it'll be less weight than the first one. And then the second one, the label L2, which has 1 overlap, you're going to make that overlap's value 1/2, and then the one after it has no overlap, so it's going to be 1. So it's going to be 1/2 plus 1 over 2 is 3/4. So you'll reduce the weight of this one, but not as much. L3 has no overlap with L2, so it's still 1. And you normalize these weights, and you get like a distribution. That's your distribution for the next sample. So the next sample, let's say you select sample 2, right? And sample 2, you select label 0, right? Label 0 has no overlap with anything, right? So that means we only reduce label 0's probability. So again, instead of 1 over 1, it's now 1 over 2, which is 1 over 1 plus 1, 1 over 2. That becomes a half. Since these have no overlap, their weights don't change. The relative weights don't change. So then we normalize it and we get a new distribution, right? And for the third sample, what we do is, let's say we randomly select L2. L2 is here. We basically, what we're going to do is we are going to basically reduce the weight of L2. And since there's overlap with L1 here and overlap with L3 here, we're going to reduce our weight a little bit. So remember what happens is L2, we add 1 to the denominator. So like previously it was 1/2 plus 1 over 1. Now it's going to be 1/3 plus 1 over 2 because we added 1 to each denominator. Divide by 2, you get this new relative weight. And L3 has the overlap in the first point. So now previously it was 1 over 1 plus 1 over 1 over 2. Now it's 1 over 2 plus 1 over 2 is 3/4. So we reduce the weight. So similarly with L1, the last point is overlapped, and previously it was 1 over 2 here, but now it's going to be 1 over 3. Anyways, you add these up and you normalize, and it's the last distribution. So basically, anytime you select an example, you lower that example's weight by like increasing the relative denominator, and then on overlaps, for each point of overlap, you increase that denominator's weight. Okay, this is one way of thinking about it. So the bottom line is you're reducing the weight of samples you already took and other samples that have overlap with them. Okay, and by the way, just as an aside, I did this fancy fraction stuff with this cool fraction library. So let's say you have a fraction 5/12, so you can do 5/12 divided by 1/2 plus 11/24 plus 5/12 plus 3/4, and you can get a fraction, which is cool. Okay. Anyways, this is a hard concept, but like, okay, if you look at Lopez de Prado's code, it's really, it's a bit like hard to understand the first time you read it. So he has a few things. He has something that's called get indicator matrix and get average uniqueness. And then he has this function sequential bootstrap, which calculates the sequential bootstrap. I fixed a few things because I guess maybe he's using a different version of Python. But anyways, this is basically his code with me fixing a few things. But in the sequential bootstrap, I added like a verbose equals true to kind of like show what's going on. So let me show you another way of thinking about like what I explained here. So another way of thinking about it, and this didn't make sense when I read it the first time, and this is kind of the way I'm looking at it. So another way of thinking about it, and this is, let's say we have the exact same random selection of first you choose L1, then L0, then L2, then L3. So another way of thinking about it is like this. I'll explain this, and then I'll explain these parts of the code. And this is a bit tricky. Like I kind of regret doing this video, to be honest. But okay, so like basically for the first one, what happens is like, let's say you're gonna just assume that all 4 of these from 0 to 3 are their own world, right? So on their own world, the average uniqueness is each 1 because it's in its own world. It's just 1, right? So it'd be average uniqueness is 1 because it's the only thing, right? So then you're going to randomly draw a sample proportional to that average uniqueness. So basically each one gets a probability of a quarter, right? So then what happens is you randomly select this example, this one example, right? And then what happens is, like, you see it's here. You add that example to the left side of it here and to each of these guys. And you still look at the average, the uniqueness of this rightmost thing. So the uniqueness here now becomes less because there's overlap, right? So you calculate the average uniqueness of this. And now for each of these, you calculate their average uniqueness as if you like, they're in their own world, but you added the first sample. And as you see, like this average uniqueness will be a lot less because it's a perfect overlap. But here, it's the uniqueness is basically still perfect 1 because there's no overlap here. Sorry, means label 1 and label 0. Sorry, this is label 0 and this is label 1 and this is label 2 and label 3. So basically here we still added the thing we sampled, which is this thing, and the uniqueness of this thing is still 1. So this will still have like a probability of 1, and then this you lower the probability because the uniqueness is smaller, and here you basically lower the probability because the uniqueness is smaller because you still have some overlap. Again, you added this sample to the side here. And similarly with here, you added the sample to the side here, but there's no overlap, so it still have the same weight. And then, I'm sorry, it's a little bit hard to explain. I might redo this video, but anyways. So then you randomly select another thing. We selected the example 0 in our example. So then you add a zeros thing to the end here. And then you calculate the average uniqueness here, the average uniqueness here. Remember, we added this 0 thing here, right? To each of them. But you calculate the average uniqueness of the actual point, which is this rightmost point, each time. And then you get like a new set of proportional weights. You sample from that. You get another one. The last one we chose was going to be, in the example, we chose L2. And so L2 we add to the end here of each here. And then we do the uniqueness of each of these samples. And then we normalize, and that's the probability. So hopefully, it's a little bit confusing. So I kind of like, but hopefully maybe that makes a little sense. If you go through the way I did the code, it might make a little bit more sense to you guys. So basically, like Lopez de Prado in his book explains that this gives you like a lot more like unique samples, and so the bootstrap will work better. And we can explain how to implement it in scikit-learn with decision tree or with random forest. I hope you guys understood a little of what I tried to explain. Anyways, just to explain some of these functions for a second, is let's say you have a series, and the series is basically like 0 to 0 means that basically the event starts, is depending on this return, the return from 0 to 1 basically. So that's what 0 to 0 means. 1 to 4 means it depends on the return from 1 to 4. And basically 4 to 5 means it depends on the return from 4 to 5. And 5 to 6, of course, depends on 5 to 6. So this is basically the T1 in the book's notation. And then there's a get indicator matrix function, which basically will create the thing above, the example above here, which you have the 1s and 0s. This thing is not going to work, to be honest with you. If you have a big data set, you're going to have to use like some sparse type stuff. Anyways, this works. And then there's the average uniqueness function. And I just calculated it on here, but like what happens is, like, as I said, it treats each thing as individual things and adds to them. So what you're going to see in this code, this is his code, is you keep adding like, you keep adding the fee. The fee is going to be the one you selected, and then you calculate the average uniqueness. So like, you keep doing that. So the average uniqueness, like in the first iteration, is just going to be like of the original points. In the second iteration, we selected point 1. So it's going to be average uniqueness of this guy, average uniqueness of these two, average uniqueness of these two, average uniqueness of these two, and then you normalize that and get a weight. And then you select a new point, The new point is, we said it was this point. We add it to here, 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 and here. Do the average uniqueness of here, average uniqueness of here, average uniqueness of here, average uniqueness of here. And then we go to the next point, do the same thing. We randomly select this thing, I think. We add this point. Oh, sorry. What was the last point we selected? Let's say we randomly selected the second point, right? Whatever. We randomly add it to here, here, here. Anyways, I don't know if that made anything clearer. I might redo this video. Time to go to sleep. Have a great day, guys.